Good morning. I'm doing this one completely full screen Wolfram Alpha for a couple of reasons, but mostly because I need you all to realize that just knowing this stuff is there anymore isn't even enough. You can start to really keep track of how much it changes. So I noticed that when I was just doing that last introduction to integration, where in fact I realized that you could go ahead and actually put in symboloids. So I noticed that I wanted to, for instance, integrate. Perhaps the function was x squared times the sine of wx with respect to x from 0 to 4, and I realized it did it. Now, that's powerful. In other words, you can put symbolage in here and it includes your algebraic symbolage. So there's incredible amounts of power that are in addition to what was here not only, 2 months ago or 3 months ago. So this starts very quickly to approximate the power, though I'm sure the power of Mathematica continues to be much larger and getting much larger. And that got me thinking about a couple in class that kind of saw this right away as, yeah, this is something. It's a great way to do cross products, which seem to be a fair bit of structures because torque is everything. So here's what you've got. If you basically can do your cross, if you remember cross, in this program an open bracket, and let's just do basically the cross product of, let's say the reaction is out. Remember the squigglies are the list. It's a 10 and 0, and we'll call that now R. I'm sorry, 10, 0, and 0. Close that up. And the force, if you remember, perhaps was going to be 0 in the x, 0 in the y, and I'm just going to call it z in the z. Now, I don't know if it'll take, you probably don't want to use z. I'm going to go r here, r in the z, and even r probably isn't that good because it might be read as radius. I'm going to close that up. So that, in effect, what we've done over time is we've put a 1 in there as our signal, and that's what we should continue to do. But let's see what it does with this value here. And it should be something like 10J or something. I don't know. We'll see what that looks like when it comes up. There it is. Minus 10J. So 0x, minus 10y, and 0k. IJK. So it gives me a value here. Now if I go back to here and put in 1, of course this is what we knew. We were doing that with an asterisk, figuring out what the moment was, and then you realize the moment of that was a minus 10. And this, of course, we're doing it in a 3D. Now I'm going to go here and try it now in 2D, and that would then shift. It won't for us. It would then shift, even more importantly, how quickly we want to shift into Z, because if it doesn't work so well in this program in 2D, then maybe we want to start working more in 3D. And you see it has a bit of an issue with it. I just want to point that out. So that's a reason why you probably, one more reason just so you know, to shift into 3D if you start to see the tools that are available in this. Now what I came in to talk about is the fact that it'll actually do integration and differentiation. So I'm going to do integration, integrate, and this you open with the parentheses, and I'm going to integrate the function x squared with respect to x, and just close it up. So, and that's going to be something called an indefinite integral. Now, I would tell you the best combination to these two videos are to go out and watch Professor Elvis once again and realize that this is not to get around the concept of shapes and calculus. It's to get you into the concept of shapes and calculus and statistics and to the language eventually that was forming towards the very end of this basically course, where you do want to know what the integral symbol means and what the differential symbol means. And it ties back to a lot of different things. So integrate here. But now let's say I wanted to integrate not only that, I had something like a times x squared, right, from 0 to 5. right? Once again, I've added some symbolage. Let's see how it does with that. So I've added some variables in there, and it gives me a value here, 125 wavelength. This is extremely powerful. I almost can't express, and the power I see in this is not so much that you can do this now, but it couldn't do it before. And so they had held back on some of the capabilities, and perhaps, once again, they will pull it back. But the other data point in this, and the fact that when they put out this app for the iPod, originally it was like $40 or $50. That was just something that caught people's attention. I don't know if they're thinking about this or not, but now it's $2. And if you notice here as I finish up, I'll make this one short. Again, integrate, differentiate. It's getting you to the mathematical form. Basically, this is teaching you some mathematical form. And cross. Those three things, just for that, it's worth learning and playing around and getting with this, especially when you start thinking about the fact that if you can sketch out the load curve, and in the end, the load curve can be a set of functions. The load curve could be, 5, at points, and it could have a function. It could be a bunch of different things. So you actually can integrate or differentiate functions individually, and this program would do that. So just to realize that the integral of the load curve the shear curve equals the initial shear, which is the reaction at one point, minus the integral underneath the load curve. And then the moment curve is the integral, or the change in moment between any 2 points is the integral underneath the shear curve. The integral underneath the moment curve between any 2 points divided by the rotational stiffness gets you a deflection angle, and that integral once down below with some integration constants gets you the actually deflected shapes. I think at some point we talked about the things that affected the stresses in a structure, and the shape of the structure were that mathematics and then the boundary conditions. In other words, if something is fixed, it's going to keep a certain geometry. If something is a pin joint, it's going to keep its X and Y and Z position, but it's going to potentially allow rotation. If something is a ball joint, it will keep its X, Y, and Z position, but allow rotation about all axes. About pitch, roll, and yaw. Remember, moment is a vector, and we can prove that here by just doing a cross product finally. We're going to do a cross, open hard bracket, open a list just like we have in our calculator, and I'm going to give the first one, I'll see if it does this. I'm going to say R1, R2, R3, close the bracket. In this case, I'm using comma, open. I'm going to call it F1, F2, F3, closing the bracket, closing the hard bracket. And I'm using this, my R is my X, Y, and Z. I don't think the program is going to like if I use X, Y, and Z, or even RX, RY, and RZ. I think it's going to think it's something it isn't. So I'm going to take and throw that, hit that return there. See how hard it works. And there you have it. It kind of gives you, right, what the components of the vector are in a format that doesn't necessarily work. So let's see what happens if I do this. RX, RY, RZ. In other words, those are the components of the radial vector, Fx, Fy, Fz. Let's see how it deals with that. And it doesn't know what to do. So once again, you start to learn how to get around the software. It's looking for a person. The format looks correct, so it's just the fact that when it sees this RX and FZ, it starts to think it's what, X, Y's, and Z's. So you start thinking about way back to the calculator when you thought about some reserved inputs. So once again, learning how to go about, for instance, you might know R1, you might know the next two. The next two might be something like 7, and they might be something like 9. The next one might be F1, sorry, I ran out of time here, F1, F2, F3. In other words, you have 3 things there. You start to have some, more unknown components of the force, but you kind of know where this is at, but not how far along. The next thing would be to change this to time, just so you know. And that would be something moving across at a certain position in X and Y on a 3D structure. So I'm going to hit a button here and realize it does it for you. Thanks for listening. I hope you get a chance to use this, play with it post-college. It came up, I guess, in the last 6 months that you were around. We've exposed you to it. We hope you enjoy it. Thanks for listening.